So up to this point, we've talked about the idea of the best guess for the next birth weight is going to be based on the mean. And that is because it is the best long-run predictor of what the next baby's weight is going to be. And that's our expected value. Now we want to think about, okay, so now suppose we can bring in some other information. So as an example, we can say, what was the mother's weight? So if the mother's weight is related to the baby's weight. So maybe the mother who's really low in weight is not having enough nutrition, and it's going to lead to a lower weight baby, as an example. So let's bring in some more information, which is the mother's weight. So if we look down here, I've got a scatter plot, which down here on the x-axis, we've got the weight, mother's weight at the last menstrual period, and on the y-axis, we've got birth weight in grams. And if you want to create this in Stata, there you go. It is the simple syntax. So let's think about, okay, so now we have some additional information that's beyond just what is the distribution of weights. Okay, we can correlate this or relate this to this weight at last menstrual periods. I want you to think about, well, now what is the expected value? Because when we were ignoring the x-axis and we were just looking at the y-axis, our expected value is somewhere in here, right? That's what it is. But now we want to think about, well, there's going to be an expected value of birth weight when a mother's weight is 100. So if you take that there, we just go up there at 100, we can take the average weight for babies whose mothers were at 100 pounds prior to their last menstrual period. And we could look, there'd be another one here, there'd be as many, because this is a continuous value, there's actually as many as you want. But the idea here is there's going to be different expected values. Okay, so now if we look again at this, we've got, looks like kind of a positive relationship that as the weight of the last menstrual period is going up, so is the birth weight of the baby. And what we're going to find is that these expected values for birth weight are going to follow this line here, and it's going to be called the regression line. So what we need to find is, what is the best line that describes the relationship here? We're going to find that at 100, the expected value is right there. 150, it's going to be there. 200, it's going to be there, and so on. Okay? And so that's really great, because now we get more precise predictions. So then we can say, okay, now I want you to predict the next baby's birth weight. What's cool about having the regression line is now I'm going to ask you, what's the next baby's birth weight? So before you just had to base it on nothing else but what the overall mean was. But now I can say, what's the next baby's birth weight? And I'm going to tell you that the mother is going to weigh 150. So then you can follow this regression line. You can make a guess as to what it's going to be. Or I might say that the mother's weight's between 100 and 150, so say 125. And that's going to be a different expected value. So by incorporating information from another variable, we can make more precise predictions. And that is the benefit of regression. That's what we're up to. So let's think about lines. This take you back in the Wayback Machine, back to say junior high or high school when you took algebra. The formula for a line is y equals mx plus b, where m is your slope and b is your y-intercept, and y and x are your two variables. And in this case, we've just done x as the x-axis and y is the y-axis. So x is going to be your predictor variables in regression, and y is going to be your outcome variables in regression. Okay, so what I've drawn here is the line that's described by this function right here, y equals 0.5x plus 1. Okay, so let's talk about what the slope means. Right? If you think back to again back to algebra, usually means rise over run. So it's the change in y, given a 1 unit change in x. So as x goes up by 1, y is going to change by 0.5. You can see that right here, right? Like, so if we look at 1, y is 1.5, right? If we draw this over here. And then as we go up by 1 unit here up to 2, y is now 2. 3, 2.5. So this difference here between here and here and here and here is always 0.5. Okay, so that's your slope. 1 is your y-intercept, right? And that's going to be the value of y when x is equal to 0. And that's because it's where it intersects the y-axis, right? So when x is 0 down here, it's going to be this value, and so it's 1, right, in this case, right here at 1. Okay, y-intercept, value of y when x is 0. Okay, so those are our lines. So let's go back to our scatter plot here. And I want you to think, okay, we've got this spread of data here, right? This cloud of data in the scatter plot. Our question is really which line, how do we come up with a line that describes the data? Because if we look back here, right, we've got numbers that go with the slope and the intercept, and so in order to define a line, we need to know what the slope and the intercept is. Because if you think about it, we could draw any number of lines through here, right? We could draw a straight up and down line, we could draw a horizontal line, we could draw that way, right? And each of them would describe certain kinds of things about this data. But that isn't really what we're going to do. And what we're going to find out is there is one and only one regression line per set of x and y variables. Okay, so if we can draw any number of lines in there, how do we pick the best one? What we're going to do is we're going to find a line, and I'm just drawing a line. I don't know if that actually describes it the best. We're going to find a line that's going to be the best predictor on average. So it's just like what we did in our simulation with the mean. We want to find what line's going to most often get us as close as possible to the actual value in the data. Sometimes our predicted value or our expected value is going to be a long way away from the actual value. Sometimes it's going to be right on it. Sometimes it's going to be really close. Okay? And the best fitting line will do that the best across everything. Okay, so on average it's going to be the best. All right, so the name for this line is the regression line. Okay, and you can think of it as the spot or the place in the data that gives you the best prediction of birth weight. So this is birth weight over here. It gives you the best prediction of birth weight across all values of mother's weight. Okay, so it produces those expected values at each of those spots of mother's weight. Our way of writing this equation is like this. So the way we'd say this is birth weight is a function of an intercept, a slope, and some errors. Okay, so beta naught or beta 0 is the intercept, beta 1 is the slope, and epsilon I is the error. Now I here, you see it in 3 places. It's an index. Okay, so this is the equation for one person. So you might say one baby's birth weight, so any given baby in this, his or her. So you might say one baby's birth weight, their weight is equal to an intercept, a slope, times whatever their mother's weight was, plus some error. We'll talk about what each of those pieces are. Okay. So I is going to range from 1 all the way to the number of people that we have. So you would have a unique value or a unique equation for every person in the sample. But note, when I say that, what's going to actually change? What is subscripted by I? This isn't, and this isn't. So these values are going to be constant no matter what person we're talking about. But each individual in the data set has their own birth weight. Each individual's mother has their own weight, and each person's error is going to be unique. And you'll see why that's the case here in a second. Okay. So let's write this in terms of expected values. Okay. So remember, the expected value for someone whose mother was 200 is right here on this line, right there. Okay. The actual value of someone who's 200 is like right there, right? Okay, so the expected value and the actual value are not going to be the same thing because we don't get perfect prediction. Okay, given that, so let's think about what that means. So the way we say this is the expected value of birth weight given a mother's weight is equal to an intercept plus a slope times the mother's weight. Okay? So the expected birth weight, given that this pipe here, this line here just means given. So the value of birth weight, given that we know the mother's weight, is equal to an intercept plus a slope. Okay? Times whatever that mother's weight is. So we're actually, when we compute that expected value, we're going to plug a value, whatever the mother's weight, so we could put 200 in that there, right? Then it would be the expected value given a weight of 200 is that. Okay. Another way to write this is, instead of writing the E, you put a little hat over this. So it's just to say the predicted or expected value of birth weight is equal to the intercept plus the slope times the weight. So that's in terms of our specific example. You can look over here in the general. We've got the same thing going on, right? We've got the expected value of y given x, function of intercept plus a slope, and then we have it with the hat over the top of it. Okay. Right now, we're only dealing with a single x value, but regression can be expanded to have many x's. Okay. When writing regression equations and things like that, we make the distinction between population parameters and sample statistics. So population parameters are things going into the population of people that we're interested in making inferences to. So in the case of predicting birth weights, we're interested in, say, the population of babies born in the United States, or you could even say over the world. It really just depends on the specific population you're interested in. And so we could think that across the entire population that we're trying to make inferences to, there is an intercept and a slope that describes the relationship between mother's weight and baby's weight. So to talk about a population parameter, we typically write them in the Greek like this. So beta naught and beta 1. Population parameters are by definition unknown. If you knew them, you wouldn't do the study. Okay. We use samples to study populations. Okay, so we get a sample of babies to try to make an inference about what's going on in the population. Sample statistics are still intercepts and slopes, but they're written a little bit different. So usually, and what I'll do most often in this class is just write them with the Roman letters. And so B0 and B1 are your sample-based estimates. And so that's what we would be computing based on our data. Sometimes you'll see the same kind of thing happening by putting a little hat over beta naught or beta 1 like that. And that, again, is just the idea that it's estimated. And just to give you an idea of sort of how things are written in populations and samples, in regression you got beta. For regression slope you got beta 1. In the sample it's B1. Mean, this is the Greek letter mu, and or we might, in the sample we'd say x bar. Standard deviations and variances are written using the sigma. Variance being squared, and then the sample standard deviation and variance is S and S squared. Population correlation is usually written with the Greek rho, with the sample being R. With factor analysis, we often the thing we're estimating is a factor loading, and the Greek letter lambda tells us what's going on in the population. There often isn't a specific Roman term for that, and so we use lambda hat. Okay, to compute these things, we're typically just going to let Stata do the work. Okay, and it uses matrix algebra to solve for the slopes and the intercepts. But if you want to see what the intercept and slope, like just a simple calculation would look like, here's an example. So with the slope, if you know the correlation between y and x, so if we know the correlation between birth weight and mother's weight, and we know the standard deviation of birth weight, we know the standard deviation of mother's weight, we can compute the slope. Once we know the slope, we plug it in here, then we use the mean of y and the mean of x, and that'll produce your intercept. Okay, so to compute this thing in a Stata, we're going to use the regress command, and we'll go through this in class a little bit more. The regress command stands for regression. Okay, so it's just regress, and then what you do is the first thing you do is put the dependent variable or the outcome. So in this case, it's birth weight, and then right after that is your x or your predictor variables there, and so that's mother's weight. Okay, this is the output from the Stata command. Okay. We're going to talk about each part of this output throughout this lecture, so don't worry about this part and don't worry about this part right now. Instead, we're going to go down to this piece right here. Okay. So our first piece is the slope. Okay, right here. This is the slope describing the relationship between mother's weight and birth weight. The way we interpret that slope is that a 1 unit difference in x, remember x is mother's weight, is associated with a B1 difference in y. So that's birth weight. So looking at this, we'd say for every 1 unit difference in mother's weight, we expect the baby's weight to go up by 4.42 grams. Okay, so I have said that the interpretation of a slope is that a 1 unit difference in x is associated with a B1 difference in y. Okay, so let's think about what that means. So this is an example from the textbook. So we've got education on the x-axis, that's number of years of education, and attitude towards psychotropic medications on the y-axis. Okay, so the expected value of attitude when education is 10 falls right on this regression line. Okay, so it's right there. The expected value for attitude when education is 11 is right here. Okay, so when we're talking about a 1 unit difference, talking about the difference between 10 and 11 years of education, and so that's represented here, right? That's that delta x is just the change or the difference in x, and that's 1 unit. So the increase from here to here is represented by this line right here, right? That's just visualizing what that change is, and that change or that difference is B1, so that's our slope. Okay, so as we move 1 unit this way, we go up by B1. So what that means is if we move 5 units, so if we go from 8 years of education with the expected value there to 13 years of education with the expected value there, we're moving 5 units on education. Then the amount that the attitude goes up, or the difference between these 2 points, is the slope times 5. Okay, because we could say that this one is B1 times 1 because it's just a 1 unit change, so it's the same thing. Okay, So you can, anytime you want to talk about anything more than just a 1 unit change in x, then you just multiply however many units by the slope. So if we want to say 2 units, then we'd say b1 times 2, right? 2 years of education. If we want to say 20 units, we'd say b1 times 20, and so on, okay? And so that's what's pretty great about a regression model. It's also its limitation, because it's going to assume that no matter where the 1 unit is, if it's the difference between 8 and 9, or the difference between 12 and 13 here, it's going to produce the same difference or change in attitude, and that's going to be B1. So now what I'd like you to do is I'd just like you to just quickly pause the video, take a look at this number, and make sure that you can put the interpretation into your own words. Okay, so make sure you can say it to yourself. Say it to a roommate or friend or spouse or whoever you're around. Just say, you know, the interpretation is, and make sure you can say it. And if you have any questions, make sure you notify me so that we can make sure we get it straightened out. Okay, our other coefficient is this guy right here. That's your intercept. Okay, Stata labels it as a constant. That's because it doesn't change in relationship to anything else. Okay, so it is our constant. The intercept is just like what it was in algebra. The intercept is the expected value of y when x is 0. Okay. So what we'd say here is when the mother's weight is 0, I realize that doesn't make any sense, but just bear with me for right now. When the mother's weight is 0, then the expected birth weight is 2,369 grams. Okay, plus some change. That's the correct interpretation. Now, it may make no sense for you to think about mother's weight being 0 pounds, because then the mother doesn't exist, right? Okay, so, but that doesn't change the interpretation of the constant. It'll still be what x is when it's 0, because Stata doesn't know. Stata's dumb in this sense, because it doesn't know what your variables mean. It doesn't know whether 0 is a sensible value or not. So when we have a nonsensical 0 value for x, what we can do is what's called mean centering. Okay, and so what I'm going to do here is I'm going to recenter the variable last weight. Okay, so if we summarize last weight, then we see that the average last weight was 129.82. So what I can do is I can generate a new variable, and we're going to call it LW underscore C. Okay, so that's the centered value of last weight. And what that is it's the observed last weight minus the mean, okay, which is 129. And a shortcut for doing that is doing it like this. You summarize and then you subtract the returned value. See the textbook for how that works, or ask me in class and I can show you some more. Okay. So what that will do is think about what a centered value would mean. So if last weight equals, for person I, so an actual observed value is 129.82. So if the centered value is going to be 129.82 minus the mean, which is the same value, 129.82. So it's going to be equal to 0. So what that tells us is on the centered value, it's now centered around 0. It's centered around the mean. So what this tells you is that if you have a 0 value, you're at the mean. If you have a negative value, you're what? Below the mean. If you have a positive value, you're above the mean, right? Okay, so I've gone ahead and rerun the regression model, and now we have last weight centered in there instead of up here. You can see it was just the uncentered version. Okay, very little is going to change in the output, except now the constant's going to be a different number. So up here it was 23,069. Now, or it's not 23,000, 2,069, and here it's 2,944. because it's still the value of birth weight when x is 0. But now x is 0 means when mother's weight was at the mean.